Okay, just to refresh, we're doing practice exam 2, problem 1. The question is, what is the rate at which C2H4 is being generated? They give you the rate of consumption of C4H4 at 4.5 times 10 to the minus 4. Okay. When you look at this problem, ignore all the rate information and treat this problem, if you see it, just like a mole problem, where if they said you had 4 moles on one side, how many would you have on the other side? All that other extra stuff, moles per liters per second, don't worry about the liters per second, because if you look at the answers, they're all liters per second. So you get rid of that, now it becomes a mole problem. So what you want to do is look at it in that regard. So if you had 4.5 times 10 to the minus 4, let's see.
Oh, no.
You had 4.5 times 10 to the minus 4 moles. And they want to know how much of this is generated. You would set it up just like a mole problem. You would have, what do I have? I have 4.5. Let me write a little bit bigger so other people can see it. And again, you want the mole ratio on this side. So the mole ratio would be over, okay, and this is all moles, and the mole ratio is 2 to 1. Everybody see that? So the answer is going to be 9 times 10 to the minus 4 moles. These are that simple. These are that simple. You can be guaranteed you'll get one of these on the test. You won't get more than one, but you'll get one of these. And if you just, forget about all the rhetoric about rate, because the rate is a function of the reaction, but you just treat it like, here's what I have. 4.5 times 10 to the minus 4 moles of C4H8. I want to know how much of this I generate. Okay, does everybody see it?
So how, I'm still green as grass with the TI-83. How would you input that in? Right there, was it 4.5 E, capital E raised to the -4?
I would have to see the calculator, but it would pretty much it would be 4.5 times e to the minus 4.
Mm-hmm.
Parentheses times 2.
Okay.
Remember, we're not going to be getting into a point during this test coming up that if you don't put the parentheses around your stuff, you're going to get wrong answers half the time.
I put my parentheses on my other exam, and I got the right answer.
Well, if you don't, mine was if you don't.
I know, but you looked at me because you know I'd forget about
You just get more sensitive. Not this time. I'll let you know when I'm looking at you, okay?
Okay, okay. Last time I forgot about it.
Yeah, well, last time I gave you help too, but that's okay. But these are that simple, okay? Okay. Another thing, problem 2. Again, you're going to get something like this on the test, and what you need to do is go to a table on page 637, table 13.2, and put that on your flashcard. Okay?
Page 637.
637, and it's table 13.2. You'll get a different version of it. Again, if you, she may or may not do it, but that's, rather than trying to figure it out automatically, you'll see what it is, because they have the way that thing is, they say they have,
I can pull it up on the screen.
no, we don't have to do that. I think everybody can sort of
Okay.
get it. If they can't, when they come in next time, we'll talk, all right?
Okay.
But it's really that's the second problem. Now I'm going to do a little bit of a review for you that I'm sure Dr. Eads already went over, but I will do it because I'm not sure what she covered, and this way if we do it, okay, I'm doing problem 3 on her practice quiz. And this is something I want to talk to everybody about. Chapter 13 is about rate law, okay? And that's worried about reactants, okay? What are reactants? On the left side. On the right side are products. The reason I say that, chapter 14 is going to talk about equilibrium, which is going to be reactants and products, and students often get them confused. So what I want to share with you is, when they talk about rate law, they're going to ask you orders, okay? The coefficients on the left side are not, and I don't know if Dr. Eads is going over this, necessarily going to be reflective in the rate law. If it's equilibrium, they will be. In the rate law, they may or may not be. Coincidentally, 50 to 75% of the time, they are the same one, but that 25% of the time, you can't guess it right. And why am I saying that? These problems we're going to go with, 3 are easy, straightforward. Getting the rate law from the experimental data, which I think you'll be doing in one of your labs, is much more difficult because the book, in my opinion, does a lousy job and confuses you. And most instructors just take the PowerPoints from the book and give them to you. So I'm going to short circuit the book if we get a chance. And I'm assuming everybody wants to be out here about 12:15?
Yeah.
Okay. I mean, you're all hungover from the Super Bowl, I can tell. Okay. All right, so let's talk a little bit about, before I get into this, is rate law. The rate law equation is rate is equal to K times,
Concentration of reactant A and concentration of reactant B.
and let me rewrite this larger, K times, I'm going to call this M, to the A, a little different than what she did, N to the B, and O to the C, okay? Let's talk about what these mean. The brackets mean concentration, okay? To the raised to the power, okay? Okay, so that's what that means. This is, like we'll call it this possible answer, rate is equal to K times NO. This is a possible answer, not the right answer necessarily. Okay? What this says, the rate of reaction for this equation, and it's equation specific, is, and this is the rate, is equal to K, which is a constant, times the concentration of NO squared. okay?
Which would be the second order, right?
Right. And you're a little bit ahead of me, but that's good. Yes?
Aren't you squared?
Oh, this is just one of the answers out of the,
Okay, but I'm asking, like, is there always going to be a 2 there, or what would that number change?
it's gonna be a function of the experimental data that you will not have access to, so they have to either tell you in the problem, or they give you the experimental data to calculate. If you see this one, I'll get into it, they'll say it's gonna be first order in each of the 2 reactants. I'll get into that, but right now I just wanted to give you the generic description of what the rate law means. Okay, this is the power, and as I said to you, in this case, it is equal to the coefficient, right? It's not always going to be true. So that's what the generic rate law equation means, okay? So, this term is called the order, okay? With respect to the individual. So in this case, the concentration of M, I'm making these are generic, is raised to the A power. N is to the B, O is to the C, which implies that this equation, if I had it, would have had 3 components, right? Again, implies. So now, how do you know what order you're going to be in? You either have two ways. You get the experimental data, and I'll show you how to do that, or it will be specified in the problem. So in this problem, let's talk about how this problem looks. Before we do anything, let's write the generic rate law. The generic rate law for this problem is going to be NO raised to, we'll call it the X power, times O squared raised to the Y power. All right, does everybody see why that's generic? Because I don't have anything specific. Now you go into the problem, and what does the problem say? It's found to be first order in each of the 2 reactants. Okay. These are the 2 reactants. First order means, everybody see 1 and 1? Okay, so we now replace this with a 1. And the other thing, and you're not going to write it as a 1. Typically, it's just going to be written without a exponent if it's 1, okay? If it's more than 1, you will get the exponent. All right, so in this case, it's going to look like this. Everybody see that?
So when there is no raised power, it's understood to be 1.
Exactly.
If you have more than 1, it just shows like 2 or 3,
Whatever it is, okay? All right, now the overall rate is always the summation of the exponents. So the overall rate here is going to be what? 2. All right, everybody see that? She's covered this so far, right?
Yeah, a little, it was at the very end class.
Okay, so let's make this a little more, not difficult. This is 2 and this is 3. What's the overall rate? Again, this is straightforward. So now we look at our answers, and it's pretty obvious now why B is the answer.
Yeah.
Okay, the other thing, for how Dr. Eads will be teaching this class, the rate laws will not be negative exponents, nor will they not be whole numbers. Okay? They will always be positive numbers at this point when she's teaching it, okay? So, again, that's pretty straightforward. So okay, we're now problem 7. A reaction has the rate law. I'll write it up here. Rate is equal to K times A times B squared. So the question is, what is the order reaction with respect to B? 2, right? What's the order reaction with respect to A? What's the overall rate? Pretty easy, isn't it? The biggest problem everybody's gonna have, they're gonna read it too fast. But this is pretty straightforward stuff. Okay, now let's talk about something that she hasn't covered, but I think will be good for you, that if I cover now, when she goes over it on Wednesday, you'll be able to not rush through it, okay? And we have about 20 minutes. Because chapter is starting, let me just see, problem. Okay. Problems 1 through 7 is probably what she's covered. She'll be talking about the integrated rate law next lecture. So let's talk about how to solve some of these experimental problems, because you'll be doing these in the lab, so it won't hurt to hear it from 3 different people: me, your lab instructor, and Dr. Reeves. And then you can pick which way you want to do it. Okay? Now let's see, I want to pick one this. Okay, let's do problem 4. Okay. First thing I do is write the equation. And this is problem 4 again on Dr. E's test. Okay, again, we're going to look at the raw data. This is the raw data. This would be the data you would get when you did your experiment, okay?
This problem, right, are we like trying to get matching pairs of it, right there, for example, for run 2 and 3? So
Yes.
There's an n, you got point 2 and point 2, and so you take m and divide it by, and
Yeah,
point
that's,
2 over.
we're going to get right into that, but what I want to do is just walk ourselves into it, okay?
Okay.
No, you're exactly right on, and that's the way I'm going to try to show it. Okay, the first thing I want to do, and this is the way I think, I always write the generic rate law. So the generic rate law is going to be this one. Okay, everybody understand that? Okay, now, let me straighten this out a little bit, because I can't write straight. Did Dr. Eads get into this yet?
She just touched on it, just barely.
Okay, so what we want to do is look at the data in a fashion that holds one of the components constant, because then the rate of change is going to be exclusively due to the component that changes. Does everybody understand what I think I said? Good, you're not the only one. Okay, what I'm going to do now is look at the experimental data here. Okay? Let's look at run 1 and 2. You look at them in pairs, okay? if we look at run 1, run, and 2, M does not change, correct? So the change in the rate, isn't that just due to the change in N? Does that make, it's because I try to just talk about it generically, and that doesn't ring any bells. When I show it, it makes a lot more sense. Okay, so this change is exclusively due change in N, right? Okay, so when we collect the data, we want to set it in this equation. Now, this is something that I'll explain to you why I did this. What this is saying is the concentrations in the data raised to a power is equal to the result of the concentrations of the rates from, we'll call in this case experiment 2 divided by experiment 1. And this will be the concentration in experiment 2 divided by 1. Does everybody see that? A chance to copy this. And I understand you've seen a lot of this for the first time, so if it's not making sense to you, speak up because it's the first time you've seen a lot of this, okay? But again, I think it's easier to show doing this mathematically than trying to explain it. So again, to repeat it, this is the concentration in run 2 over the concentration of run 1 of N, right? Equal to the change in the experimental data of 2 versus 1, okay? You set it up this way. The book is going to get into deltas and everything, and I believe will confuse you. To me, just look at the data and just, I hate to say it, just follow the recipe.
And so it's only N because that's what's changing the rate, right?
Because when
M
you-
is constant.
Because we intentionally picked the data so that we only show the change in N. So now, when we divide this, and the other thing I do with these, and I recommend, always put the data so that the larger number is on top. Because otherwise you're going to be dealing with fractional exponents. And fractional exponents will drive you crazy. So when we do this, even I can figure this one out. This is going to be 2 to the y, right? And we can all look at this, and that looks like 4, doesn't it? Okay? So what's y going to be?
2.
Okay? Okay?
So
Let me ask you this question. If this were 1, what would y be?
4.
This were 1.
Oh,
If 2 to the y equals 1, what would y be?
0.
0.
Anything we say 0.
Okay? Okay. On your flashcards. On your flashcards, put that little tidbit on there, okay? So that when you get, because you know what's going to happen. You're going to forget about that and try to, and the obvious one equals to 2. What's y going to be equal to? Okay, 1, 2, you see, have that on your flashcard. You might get a third one, but again, to make it easier for you. Okay, so now we know, in this case, when we go back here, and this 2, right?
Mm-hmm.
Okay, now, so we'll see if I connected with everybody. Can I erase this now? Okay. All right, now my next thing is I wanna find M. So what experimental data would I wanna look at?
0.1, 1.2.
In 3, right?
0.03.
Okay, so now, we're gonna have 0.200. And the reason I'm calling this X is because it directly refers to this one, okay? And then I'm gonna put
X is 0.
So X will be 0 in this case. Everybody see that?
So since it's 0, will M be canceled, or, well, I'm not sure, cancel would be the proper term for that, but what
It would be
happen to-
totally eliminated.
Okay.
It would be a non-factor.
It would be a non-factor. So this now becomes K to the N squared, okay? Again, I don't know how Dr. Eads will teach the details of this. I don't know how your lab instructor will teach it. So you go through it and you decide which one is easiest for you. To me, I'm just giving you a recipe. Step 1, find the situation in which one set of data is constant, because then the change is exclusively due to the other. Step 2, raise it to the power. Step 3, solve for the exponent. Everybody good? Okay, now let's make this a little more difficult. Again, I'm referring to the lab because I can teach the lab since we're not doing anything right now. Suppose the instructor, this is a lab question, says to you, solve for the constant. What would you do? Assuming this is correct. Anybody have any ideas?
So K is constant.
Right, but this is what they want you to solve for, find it.
So would you add all the rates together?
No, but you're on the right idea. You would say, isn't this one set of data?
Yeah.
Isn't the second set of data? Third set of data? So wouldn't you just put the respective N value in here? You have the respective rate and solve for K? Okay, so here's what I'd like everybody to do. This group, take the run 1 data. Run 2 data, run 3 data. Let's see what we get for K, because if we really did the experiment correctly, K should be the same for all 3 groups.
Okay.
And I have no idea what K is going to be, but this is, again, a version you might get from the instructor. Dr. Eads may just give this to you and not cover it in, so let's everybody try that and see what we get. Yes.
How do we run? You said run K, how do we?
Okay, let me show you an example. I'll use run 1, okay? In run 1, the rate is 0.000230 equal to K times the N value, which is 0.100, right? You would square that and solve for K. So you do that, so that's how you would solve, this is for run 1. I want everybody to do this because I want to find out how many people's will have problems with this using their calculator. You shouldn't, but if you don't use, what's that here?
Parentheses?
Did you get a value for K?
Yeah.
What'd you get?
0.023.
0 point,
0.
did I do that right?
Yeah, I got the same thing.
Yeah, but there's is, the point is in between the zeros.
So it should be
Yeah, there you go.
like that? You get that?
I got the same thing.
Okay, that, what does that tell you?
And did it right.
That experiment is, the data is right, the experimental data is right, because K will, you know, if you're on a test and you're not sure, just try K's for both you'll get the same answer if your rate equation is correct. Because the rate equation, again, is specific to the data that you have. Now, they'll give you something fancier than M or N, these are just generic terms.